Introduction. Raj and Amar are sitting in the drawing room. Raj is reading his favorite book and Amar is doing some work. Amar, I want to ask you something. How this calculator works? How every time it gives the correct result? Okay, Raj, I will tell you. Calculator works on the combination of diodes. Diode is a semiconductor device and it can be used for on and off purpose. When the diodes arranged in a particular manner, then they give specific logical result. Okay, Amar, now I understand the basic concept of calculator. It's quite interesting and I want to know something more about it. Students, today we will study about the semiconductor electronics. Objectives. At the end of this lesson, you will be able to know about energy bands in solids, define insulators, semiconductors and metals, understand intrinsic and extrinsic semiconductor, define N-type and P-type semiconductor, understand P-N junction, describe semiconductor diode, analyze forward and reverse biased junction diode, analyze VI characteristic of PN junction diode, define rectifier, explain Zener diode. Energy bands in solids. Electrons in an atom are distributed in various shells according to certain scheme and they are allowed to possess certain discrete energy values. The permissible energy values are usually shown on an energy level diagram. We consider the formation of bands for the energy level normally occupied by the valence electrons and the next level above it. The interatomic separation is supposed to decrease gradually from infinity to R, not corresponding to equilibrium separation in a crystal. Valence band. The valence band is a band of energy levels occupied by the bond valence electrons of the atoms in the crystal. Forbidden gap. A range of energies above the valence band which electrons are not allowed to possess. Conduction band. A band of energy levels just above the forbidden gap which is occupied by conduction electrons of the crystal. These electrons are free to move about and increase their energies in electric field. Insulators, semiconductors and metals. On the basis of band theory of solids, the solids are classified as insulators, semiconductors and metals. Insulators. Valence band filled completely and conduction band is far away. A good example of this type of material is diamond. It has a forbidden gap of 6 electrovolt. All the valence electrons take part in the covalent bond formation and none is available for conduction of electricity. Semiconductors. Valence band filled completely and conduction band is close to it. An example of this type of material is silicon. It has a forbidden gap of 1.1 electrovolt. At absolute zero it behaves like an insulator. But at room temperature, a small proportion of electrons gain enough energy from thermal vibrations of atoms so that they move to the conduction band. The conductivity of semiconductor material increases with rise in temperature. Metals. Valence band partially filled or valence and conduction band overlap each other. An example of this type of material is sodium. When an electric field is applied across a sodium crystal, electrons in the valence band can acquire small amount of energy as higher energy levels are available. The material is, therefore, a good conductor of electricity. In a good conductor, the partially filled valence band is also the conduction band. Intrinsic semiconductor. Intrinsic semiconductor are those in which impurities are not present and therefore called pure semiconductors. In these semiconductors, few crystals defect may be present. When a semiconductor is taken at 0 Kelvin, then it behaves as an insulator and conduction occurs at higher temperature due to thermal excitation of electrons from the valence band to the conduction band. For example, germanium and silicon. Let us consider silicon, which has 4 valence electrons. In order to gain stability, it has to make 4 covalent bonds. The electrons which are participating in the covalent bonds are known as valence electrons. If some energy is supplied, then covalent bonds break. Electrons will come out and move freely, resulting in the formation of vacant sites in the covalent bonds. These are known as positive charge carriers, named as holes. The number of conduction electrons will be equal to the number of vacant sites in the valence band. Extrinsic semiconductor. The extrinsic semiconductors are those in which impurities of large quantity are present. The impurities can be either of third group elements or fifth group elements. Based on the impurities present in the extrinsic semiconductors, they are classified into 2 categories. N-type semiconductors. When a pentavalent impurity is doped in a pure semiconductor crystal, then the crystal is known as N-type semiconductor. P-type semiconductor. When a trivalent impurity is doped in a pure semiconductor crystal, then the crystal is known as P-type semiconductor. N-type semiconductor. N-type semiconductors. In order for silicon crystal to conduct electricity, we need to introduce an impurity atom such as arsenic, antimony, or phosphorus into the crystalline structure. These atoms have 5 outer electrons in their outermost covalent bond to share with other atoms and are commonly called pentavalent impurities. This allows 4 of the 5 electrons to bond with its neighboring silicon atoms, leaving 1 free electron to move about when electrical voltage is applied. As each impurity atom donates 1 electron, pentavalent atoms are generally known as donors. The resulting semiconductor material has an excess of current-carrying electrons, each with a negative charge, and is therefore referred to as N-type material, with the electrons called majority carriers and the resultant holes minority carriers. P-type semiconductor. P-type semiconductors. In P-type semiconductor, we introduce a trivalent impurity into the crystal structure, such as aluminium, boron, or indium. Only 3 valence electrons are available in the outermost covalent bond, means the 4th bond cannot be formed. It gives the semiconductor material an abundance of positively charged carriers known as holes in the structure of the crystal. As each impurity atom generates a hole, trivalent impurities are generally known as acceptors. The conduction mainly consists of positive charge carrier results in a p-type material, and the positive holes are called majority carriers while the free electrons are called minority carriers. Example on semiconductors. Let's take an example on semiconductors. A semiconductor has equal electron-hole concentration of 6 into 10 raised to the power 8 per meter cube. On doping with a certain impurity, electron concentration increases to 8 into 10 raised to the power 12 per meter cube. Let's see the solution. As the electron concentration increases, it is an n-type semiconductor. We know that Ni square is equal to product of Ne and NH, where Ni is concentration of intrinsic carriers, NH is hole concentration, and Ne is electron concentration. Therefore, NH is equal to Ni square divided by Ne. On putting the values, we get NH is equal to 4.5 into 10 raised to the power 4 per meter cube. Hence, the new hole concentration is 4.5 into 10 raised to the power 4 per meter cube. With the doping, energy gap decreases. p-n junction. If donor impurities are introduced into one side and acceptor impurities into the other side of a pure crystalline semiconducting material, a p-n junction is formed. The donor ion is indicated by a positive sign because after this impurity atom donates an electron. It becomes a positive ion. The acceptor ion is indicated by a minus sign because after this atom accepts an electron, it becomes a negative ion. Initially, there is abundance of holes in the p-type material and of electrons in the n-type material. The holes in the p region will diffuse to the right across the junction and combine with electrons in the n region. Similarly, the electrons in the n region will diffuse to the left across the junction and combine with the holes in the p region. For every such diffusion recombination event, the left side of the junction acquires a negative charge and the right side a positive charge. As a result, an electric field will appear across the junction. Since the region of the junction is depleted of mobile charges, it is called the depletion region or the space charge region. To diffuse from the n region to the p region, an electron must climb the energy hill of height eV0. A hole must also climb an energy hill of the same height to diffuse from the p region to the n region. Semiconductor diode. A semiconductor diode is basically a p-n junction with metallic contacts provided at the ends for the application of an external voltage. It is a two-terminal device. The arrowhead corresponds to the p-type terminal of the device and points in the direction of easy current flow. It is a two-terminal electronic component with low resistance to current flow in one direction and high resistance in the other. The most common function of a diode is to allow an electric current to pass in one direction, while blocking current in the opposite direction. Forward-biased junction diode. When a diode is connected in a forward bias condition, a negative voltage is applied to the n-type material and a positive voltage is applied to the p-type material. If this external voltage becomes greater than the value of the potential barrier's opposition will be overcome and current will start to flow. Forward biasing condition represents the low resistance path through the p-n junction, allowing very large currents to flow through the diode with only a small increase in bias voltage. The actual potential difference across the junction or diode is kept constant by the action of the depletion layer. The negative voltage pushes or repels electrons towards the junction, giving them the energy crossover, and combines with the holes being pushed in the opposite direction towards the junction by the positive voltage. The application of a forward biasing voltage on the junction diode results in the depletion layer becoming very thin and narrow, which represents a low impedance path through the junction, thereby allowing high currents to flow. The point at which this sudden increase in current takes place is represented on the static IV characteristics curve as the knee point. Reverse biased junction diode. When a diode is connected in a reverse biased condition, a positive voltage is applied to the N-type material and a negative voltage is applied to the P-type material. The positive voltage applied to the N-type material attracts electrons towards the positive electrode and away from the junction, while the holes in the P-type end are also attracted away from the junction towards the negative electrode. The result is that the depletion layer grows wider due to a lack of electrons and holes and presents a high impedance path, almost an insulator. Reverse bias condition represents a high resistance value of the p-n junction and partially zero current flows through the junction diode with an increase in bias voltage. However, a very small leakage current does flow through the junction, which can be measured in microamperes. Pi characteristic of p-n junction diode. In forward bias, the current first increases very slowly till the voltage across the diode crosses a certain value. After the characteristic voltage, the diode current increases exponentially, even for a very small increase in the diode bias voltage. This voltage is called the threshold voltage or knee voltage. For the diode in reverse bias, the current is very small and almost remains constant with change in bias. It is called reverse saturation current. At very high reverse bias, the current suddenly increases. This voltage is called the breakdown voltage. Rectifier. The process of conversion of alternating current into direct current is called rectification, and the circuit for this conversion is called a rectifier. The crystal diode is used as a rectifier. There are two rectifier circuits in use. Half-wave rectifier. In half-wave rectifier, either the positive or negative half of the AC wave is passed while the other half is blocked. Full-wave rectifier. A full-wave rectifier converts the whole of the input waveform to one of constant polarity at its output. Half-wave rectifier. The AC signal to be rectified is connected across the primary terminals P1 and P2 of a step-down transformer. One of the secondary terminals S1 is connected to P region of junction diode, while the other secondary terminal S2 is connected to N region with a load resistance RL in series. The output voltage is taken across the load resistance RL. The AC input voltage across secondary terminals S1 and S2 changes polarity after each half cycle. During the first half cycle of input AC voltage, the terminal S1 is positive with respect to S2. During this half cycle, the diode is forward biased and therefore the diode conducts current from A to B. During the next half cycle, the terminal S1 is negative with respect to S2. Under this condition, the diode is reverse biased and therefore it conducts no current. Hence, a potential difference across load resistance RL exists for positive half cycles and no potential difference exists during negative half cycles. And the output across load is pulsating DC. Full wave rectifier. Full wave rectifier. For full wave rectification, two junction diodes are used. It consists of two diodes, D1 and D2, whose N terminals N1 and N2 have been connected together. The AC signal to be rectified is connected across the primary terminals P1 and P2 of a power transformer. The P regions P1 and P2 of the diodes are connected to the ends S1 and S2 of the secondary of the transformer. The output taken across the load RL. The AC input voltage across secondary S1 and S2 changes polarity after each half cycle. During the first half cycle of input AC signal, the terminal S1 is positive and S2 is negative. Then, diode D1 is forward biased and diode D2 is reverse biased. Therefore, diode D1 conducts while diode D2 does not. The direction of current due to diode D1 is directed from A to B. In next half cycle, the terminal S1 is negative and S2 is positive. The diode D1 is reverse biased and diode D2 is forward biased. Therefore, diode D2 conducts while D1 does not. The direction of current due to diode D2 is from A to B. Thus, for input AC signal, the output current is a continuous series of unidirectional pulses. Zener diode. A Zener diode is a reverse-biased properly doped crystal diode having a sharp breakdown voltage and operated in breakdown region. When the reverse bias on a crystal diode is increased beyond a critical value called the breakdown voltage, the reverse current increases sharply to a high value. The Zener voltage depends upon the amount of doping. A lightly doped diode has a higher breakdown voltage. The main characteristics of Zener diode are: when forward biased, its characteristics are just like those of ordinary diode. A Zener diode is always reverse biased. When reverse biased, a small reverse current flows through it. This current remains constant up to a certain critical voltage called turnover voltage, and then current increases rapidly. The reverse voltage for which the current corresponds to some point on linear portion of reverse characteristic is called the Zener voltage. Did you know? Some materials are classified as semi-insulators. These have electrical conductivity nearer to that of electrical insulators. An example of a common semi-insulator is gallium arsenide. Silicon is the heart of any electronic device. Today, most semiconductor chips and transistors are created with silicon. The electronic areas of a chip are those treated with traces of chemicals such as boron and phosphorus, which alter the conductivity of silicon. Summary. Let us summarize what we have learned. In a semiconductor, valence band filled completely and conduction band is close to it. The conductivity of semiconductor material increases with rise in temperature. Intrinsic semiconductors are those in which impurities are not present and therefore called pure semiconductors. In p-type semiconductor, we introduce trivalent impurity to the crystal structure, such as aluminium, boron or indium. If donor impurities are introduced into one side and acceptor impurities into the other side of a pure crystalline semiconducting material, a p-n junction is formed. A semiconductor diode is basically a p-n junction with metallic contacts provided at the ends for the application of an external voltage. The process of conversion of alternating current into direct current is called rectification, and the circuit for this conversion is called a rectifier. A Zener diode is a reverse-biased, properly doped crystal diode having a sharp breakdown voltage and operated in breakdown region.